It's really a pleasure to be here. Greg sort of tormented me, giving me this task. So going to go ahead and try to summarize hundreds of years of what has been going on with this site. I've been just here half of the life of the center, but I thought of showing some of my students a photograph from a little bit before my first visit to the Blume Center. And just before I start, to just thank a number of people that helped me put together this presentation. There's a lot of history to summarize here. And sort of the theme that I want to describe is, it comes from this book that I have home with some of the words and speeches from President Kennedy, and has this foreword that was written by his brother, and basically says that it's not about the dates and the facts, but it's really about the people who did that. So I'll be basically trying to describe the people that were involved and the legacy and responsibility that we have being part of the center. So I'll go back to the Portola expedition, just to give you a little bit of frame. The Jesuits had just been kicked out of the kingdom because they got in trouble with the king of saying something, so king took care of them. And the Jesuits were the ones who had put the missions in Baja California. And then the Franciscan friars sort of saw that the opportunity to maybe take that territory for the Alta California. But at that same time, sort of similar to what we have today, sort of the spies of the Spanish kingdom in London have heard that the Russians were, advancing to the south, and they were sort of already past the triple junction here in California. So they wanted to keep them. So that's why the Viceroy sent Portola over here to California. There you see the map. And we have 3 diaries, and we know exactly what they were doing, and they're beautiful. I recommend you guys read. I've read all 3 of them. So we basically hear from Portola himself, then Fray Juan Crispi, the Franciscan friar, and then the engineer. And the engineer, Miguel Constanzo, is beautiful. I mean, he was just a master of, I'll show you some of the things that he was doing. And this is some of the handwriting that they were doing. I'll tell you, I've been faculty member for 30 years. This is a much easier read than some of the midterms and finals. But anyway, so they're making their way back. I mean, they start in what is now today Mexico. They drop Fray Junípero Serra in San Diego, and then they go by land. And on this day, on July 28th, they're camping next to a river. They pitch the tents, and they document that they experience a very big earthquake. And this is really the first historic document that we have in Alta California of earthquakes. And not only that, but they explicitly said what was the duration. They said that it lasted for half an Ave Maria, half a Hail Mary. And I should say that Hail Mary is not this thing that you see at the end of the football games, but it's this other thing. So if you're like me, you're probably trying to reverse engineer this, and you read this thing several times and how long it's taking, what's the duration. And then they also document there were 4 aftershocks that day, and then a few days later another aftershock, and probably a 6.5 that took place. And this is what we now call the House of Anaheim, that the Germans put that name sort of close to Mickey Mouse and Mimi's home. And then they proceed to the north. And this photograph that you see there is here from Portola Valley, where they first see the bay. And but the interesting that happens on November the 4th. But November the 5th is very important for Stanford, because then they come south and they camp right next to San Francisquito Creek at the foothills. So you read this description and say, wow, they're camping on Stanford. And this is the first map of the bay, and I'll just sort of rotate it and put some names so you recognize this. But the maps that this guy, Miguel Constanzo, was doing, they're just blind modeling. Just to give you an idea, you probably know that GPS technology was developed here at Stanford. What you don't know is that this guy was giving the coordinate of Stanford with 3 decimal points 100 years before. And just a little bit of the map of the Bay Area that he put together, sort of going on horse. I'm a structural engineer, as you know, so we like connections. These are some of the connections that I talked in class. I want to talk 3 connections today. The first one is, you may not be aware, but there's a super strong connection between astronomy and earthquake engineering and seismology. And that photograph that you see on the right, I took it at Owens Valley. And it's a really dark place and sort of really cool. I actually wanted to be there at 2:30 in the morning because that's the time of the earthquake. And you would think that it's very, quiet out there, but actually those machines are extremely noisy, and obviously the astronomers are operating while you're taking these photographs. But anyway, this is, I talked about the first earthquake that was historic, that we have documentation. This is the first earthquake where there was an investigation. There were very 2 detailed investigations. They document what happens at every house, the people that die, and the effects. And we have this also historic evidence from John Muir, the Scottish friend of ours, that basically started the Sierra Club and Yosemite Act in Yosemite. Really the start of the national parks, America's greatest idea. And he's out there, he's never experienced an earthquake, and basically says, whoa, this is different than anything that I've experienced before. And he goes out of his cabin and says, a noble earthquake. But this was 200 kilometers north. So we don't know, there were no instruments back then, so we didn't know what was this. But some people have estimated this earthquake to be one of the strongest in California. Some people say 7.4, 7.6, and I've read some people estimate as large as 8. Connection number 2, and this is, you may think this is a strange one, but it's between pianos on the East Coast and earthquakes in California. And the connection is this gentleman that hopefully you've heard about. Some of my students have heard me talk about this fellow for 4 hours. I've read a lot about him. But, probably Billy Joel would describe him as Piano Man, right? Everybody knows that the song Piano Man. But basically, this guy, fascinating story. You got to read about it. You can skip dinner to that night and read about him. But, one way of describing him would be sort of the Elon Musk of the time. So his sort of equivalent of PayPal was pianos, and he does all these pianos in South America, and he reads that they found gold in California, so he figures like, people are, this new rich are going to be interested in pianos. So he wants to sell pianos in California, but he finds out that they're not interested in pianos. So what he does is to go into real estate. And he makes so much money. While the 49ers are up in the Sierras, he's making tons of money. He basically at one point owns half of San Francisco and about a quarter of the peninsula. The richest man in California, probably close to the richest man in the United States at that time. And he's getting sick and sort of thinking about his legacy. And he's sort of debating whether to build a pyramid larger than Kep's pyramid in Egypt, or maybe a statue of himself in San Francisco. So in one of these gala dinners of rich people in the Bay Area, he meets Professor Edward Holden, who was the president of the University of California at the time, an astronomer. He says, what are you talking about? First of all, this pyramid is going to have differential settlements because we have fills in San Francisco and part in rock, and it's going to be so big it's not going to work. And believe me, I know about earthquakes. I've written this catalog, the first catalog of earthquakes in California. So your Colossus is going to collapse in an earthquake. So if you really want legacy, what you need to be doing is donate this money to the university, and together we're going to build the largest telescope in the world. And he's doing these drawings and what was going to be the Lick Observatory, right, in Mount Hamilton. And so that's Lick Observatory, and a 36-inch refractor. If you've never been there, it's like you got to go tomorrow there. It's just beautiful. And the thing is, like, why astronomers were sort of concerned about earthquakes? Well, they were concerned about their glass and earthquakes and possible problems of their telescopes during earthquakes. And sure enough, heavy things, and there you see the counterweights on the right. Earthquakes can do lots of bad things to heavy objects. And to the point that Professor Tsuruhira actually wrote this paper on the stability of the seismographs themselves. But anyway, there's this Scottish guy, Ewan, who's now a mechanical engineering working in Tokyo, along with John Milner. And he develops this beautiful three-component seismograph. And what was really unique about this one was it was not the first one, but it was the first one to have an accurate reading. And sort of optional reading assignment, read the description of the clock, the secondary clock of this instrument to put the tick marks on the seismograms. As just like, now we understand why we learn what we learn is this bright minds doing all of this. So anyway, the image on the right is the seismograph as it was drawn by Professor Holden, and you see the inauguration of the observatory, and then April 18, 1906, 5:12 p.m. a.m. We all know, at least the students who did the midterm on Wednesday, they know exactly what went on that day. But essentially, what you're seeing here is the birth of seismology and earthquake engineering in California and the United States. As a matter of fact, when I was at faculty here, just very recent, I read that the astronomers have found the original. And so, there was a Father's Day, there was not commencement, and they said, "Dad, where do you want to go?" "Oh, Lake Observatory. I got to see the original, right?" And that's the original. So that's the start of seismology and earthquake engineering. And you get to see the tick marks there on the lower right. You see we were there again last weekend with some of my students. But anyway, this brings us into the investigations after 1906. And there was this famous Lawson report that the governor appoints, just like Loma Prieta, competing against time. You may be familiar with that. I was a little part of that myself. But it was really, you realize that competing against time was mimicking what was done back in 1906. And that was led by this 8 gentlemen. And what you may not understand, there was no lady at the time, unfortunately, but maybe it would have been much better, the report, if it was more diverse. But anyway, 4 of these gentlemen were geologists, and the other 4 were astronomers. And one of them, of course, as Jennifer mentioned, was Stanford, right? So Professor Branner, our library here on Earth Science, is named after him. And super important document, 2 volumes, and then it has an atlas with all the seismograms recorded worldwide. And but for example, the elastic rebound theory of Reed was published there actually 3 years before he wrote his famous paper. And then Branner was very active, actually not done a lot of earthquake engineering prior to this, but he really jumped. He got to be in charge of doing all the field work, especially here on the peninsula, with one of his graduate students or student at the time. And then you may have seen all of these photographs from campus or from San Francisco, but many of those have those initials. And of course, that's Professor Branner, who, as Jennifer mentioned, became president of the university. And one of the striking things about that report was side effects. And for example, they described that from one block to another, the level of damage was very different. And it was completely different, the performance of the structures on rock than on alluvium soils. And that triggered the first experiments here on campus by Rogers, the first shake table. And I have this discussion with Bob Raderman whether it was the first one or not, but we'll leave that discussion apart. But basically it is doing these experiments which are sort of described in the Lawson report. And this is just a little connection, but Professor Branner actually sort of reviewed the paper of one of my old relatives. He was the uncle of my grandfather. And I found this just recently. I said, oh, man, I had no idea it was related to a president from Stanford. But anyway, another important person here is this gentleman, another astronomer, Professor Townley, who was very active on earthquakes and on astronomy at the same time. He's key to the establishment of the BSSA journal, who was printed by Stanford Press. This is issue number 1. And he actually, at that time they were not editors, but he was sort of the secretary of a society. And he was, probably Jack will appreciate this, but he was essentially editor for 25 years of the journal. He writes also the 3rd catalog of earthquakes in California. And at the same time, he's doing that catalog of long period pulsating stars. So pretty amazing guy. And just to wrap up of this connection of astronomy and seismology, if you sort of collect waveforms and know about acronyms, probably you'll recognize some of those acronyms are on our observatories in California. And if you think about it, or at least I've been thinking a lot about it, it's like we've been collecting biased data, at least on, sort of polluted with topography effects, at least probably the surface waves, the vertical components. But anyway, that's what we've been doing for more than 100 years. Another key person here on campus was Professor Bailey. He once made some comments about, sort of some of the comments like we sometimes make is like, we will have more earthquakes in California, and it could happen tomorrow or maybe in a year or in maybe 5 years about Santa Barbara. But he was quoted as he predicted the Santa Barbara earthquake, so became known as Lydik's earthquake. And he created this map, in the 30s, pretty close of the whole San Andreas fault, and started working on that. And then he was really into geology. He wrote a paper, a book on the geology of Patagonia. It was called A Yankee in Patagonia, and doing comparisons with seismology and the earthquakes in Chile. Of course, very very active, the subduction over there, and he was also in charge of the seismic station here on campus that was just at the entrance of a golf course, and which was named after President Branner. And so now let me move a little bit from geology corner to engineering corner to talk about some of the people that contributed. First, right after the earthquake, of course, half the campus is destroyed. So there are these 3 professors that are appointed by the president to basically lead the reconstruction. And you can imagine this took a lot of time. And that was led by Charles Marks. Just recently, I was reading more about him, and I ran into this student, Charlie Marks, and said, I sent him an email. I was like, are you related to Professor Marks? And he said, no, but I was surprised when I arrived to campus to see that there's a street under my name. But anyway, this guy is very involved. He participates in the first code in which, unlike sort of the first one, they were continuing after 1906. We were still continuing designing for earthquakes with wind pressures, which doesn't make a lot of sense, but that even after 1906, that's what we continue to do. But at least now we start moving into percentages of the weight, and that was done by him here in California, the Palo Alto Code. And then the 3rd professor was actually mayor of the city of Palo Alto, for those of you who live there. And connection number 3, and another strange one that you may not know, but it's between earthquakes in California and Denmark. So there's, this relatively small country in Europe, and non-seismic essentially, but as I will tell you, some of the greatest minds on dynamics that come from that country. I call them the Great Danes, but not exactly these. But I'll talk about 2 Great Danes, and hopefully by the end of my talk, you will agree of how great these 2 Danes were. The first one is, of course, Lydik Jacobsen. Greg knows I'm a super big fan of this fellow. I started reading when I was a graduate student at Berkeley. I started reading about this guy, and then equivalent linearization had sort of a renaissance in the 90s, and people were quoting like, Zosen and Iwan and Spanos and all these people. Some would quote Hudson or Rosenbluth and so on. It's like, no, this goes way back to Stanford. But I didn't have this paper. So when I interview here, yes, I needed to make a presentation and so on. But the first thing that I wanted to go to the library and get a copy of this one. And it was exactly as I remember with this photograph that you see here. And a lot of people don't know, but equivalent linearization was born here on campus by this gentleman. The other thing, you may find that gold it's in the Sierras and so on, but sometimes you find gold in the libraries. And I'll show you some gold that I found in the Blume Center library. This is a letter written by Den Hartog, one of the greatest minds on dynamics, when he was at Westinghouse. And he's writing to Jacobsen and says, this morning I was talking to Stephen Timoshenko, and he mentioned that you've been working on this thing just like me. And that's they're exchanging letters and sort of photocopies at the time there you see in blue and going back and forth. So Lydik Jacobsen, one of the first things that he does is go and revisit this issue of the soils. So he studies all the papers and experiments that Roger had done. And then he basically redesigns the shake table and develops a new one, but it's really to test soils. So here's a mechanical engineer doing soil dynamics, but it's like some of the first soil dynamics done with math, and he was aware of Professor Kanai's and Sasawa's work and so on, but he takes it to another level. And the reason, here are some of the photographs. So he actually develops two ways of running the table. One is with electrical motor to do basically harmonics, but he's well aware that this would be, too severe for the test. So he actually developed some transient tests by doing impact tests, which is what you see there on the lower left. And he does it, starting from rest, but also from motion and so on. And not only that, but the sensing that he develops is, I don't have time to talk about the sensing, but those of you who do health monitoring, you should read what this guy was doing in the 30s. One of the things that he does, he has two papers where he describes basically dynamic similitude. And this is way ahead. It's like Piotr Monkaras probably would appreciate this. But he basically says that in order to do this, you need to get acquaintance with the underlying similitude problems. And then he says that to do this, the experiment must not be afraid of attacking the problems from a mathematical point of view, because a mere experimentation without conscious theoretical foundation cannot be expected to yield results that will lead into safety. And Jacobsen wrote that, but as you read that, I just see one mind in my head, and it's Helmut Winkler, because he would basically tell you the two same things over and over. So here's the shake table. He's doing, the wave equations, first use of the shear beam. Some of my students know that I like beams, and now you know where everything comes from. This gentleman, and he's looking at the dynamics, first, second, third mode, and so on. And he's looking at peak responses at the surface of the soil deposit. So he's basically doing site response analysis in the 30s. But what is amazing of this is that this is like 30 years before people like Harry Bolton Seed started working on this. Thomson Haskell, for those of you who are seismologists, and he's doing all of these things without computers, by the way. And then the other thing is that, a lot of people say that got a lot of motivation from the Santa Barbara earthquake, but it's actually not true. What really triggers a lot of this work is the Long Beach earthquake. Of course, that's the accelegraph had developed, and it's the first record. So he gets hold of the first record, and he wants to run shake table tests using this record. By the way, he has other paper in which he develops the servo valves pretty much at the same time as Mogg. That in the 50s. So this is like true genius. And speaking about true genius, I basically said, this guy is like way ahead of his time and a genius in dynamics. And many years later, when the second oral history was written, John Blume describes Jacobsen exactly with the same words. And I said, I knew it. I knew it. This guy was a genius, and he was like ahead of his time. And so just to give you another sort of idea of what he was doing, so he does an integration so he digitized the record, does the integration, and then as you see there in the middle, he finds, these problems with baseline. So he basically corrects it. But what it's amazing this, and then he creates the displacement time history that he's going to use to run the table. But think about it. This is like 20 years before Professor Hudson wrote his famous paper on problems of the use of accelegrams. And the word baseline correction would not be known like for 15 years after this. But he was doing this and he was running the test. Not only that, but he's doing these experiments with SDOFs. And what he's trying to do is to get an idea of the base shear that structures would be going with this record. So he computes this graph that it's maximum shear normalized by the weight of each one of these models. And then you realize he just simply calls it a response curves. So of course, the original paper by Maurice Biot had already been written, but what most people don't realize is that he never had actually computed a response spectra for a record. So this is probably the first response spectra for an actual record was done here on campus by Jacobsen. And if you actually read the first paper in which Biot does for an earthquake record in 1941, he actually has what I show you. So he was aware of the experiments that Jacobsen was doing here on campus. And not only that, but he cites, he's wondering and he computes that for certain periods, there are going to be critical periods that are going to see much larger demands. He describes those. And not only that, but he says that, say the Palo Alto building code would be designing for 6 or 5% of its weight. And he said, notice that in these cases, this base shears, they go between 11 or 29%. And he basically adds that phrase that you see over there. It's like, we should recognize that this is way higher than we've been designing for. These are some of the photographs of that table. And again, some of the sensing that he was doing and recording and how he was recording the displacement time history of each one of the oscillators. It's amazing. So again, this is years before Hausner and Biot ever computed